section 6.3. We're still finding volumes. When we look at volume, at the first part of 6.2, we rotated about the x-axis, then we rotated about the y-axis, and then we incorporated other lines. So we learned that when we're rotating about the x-axis or any other horizontal line, we have a choice of disk or washer. Disk if you're sitting directly on that line of rotation, washer if there's some area in between. Now when you're rotating that about the x-axis, when you make these little slices, you're making those slices perpendicular to the x-axis. Anytime those slices are perpendicular to the x-axis, that tells you what you have to have inside your integral, because you are perpendicular to that axis. So like when you did cross sections yesterday, your cross sections were perpendicular to the x, you had to have x's inside the integral. Well, when we were working on one of our homework assignments, you had to find area and volume. We were working on those AP questions, and I had made a statement that really wasn't altogether true. In that statement, I told you that when you're finding the area, you can do that with respect to x or with respect to y, whichever one you feel is easier. When you got to the volume, I told you that you really had no choice. If it was about the x, you had to have x's. If it was about the y, you had to have y's. Well, it wasn't true. It was true at that moment in time, but now we're ready. We're a little older. We're a little wiser. We're ready to hear the full truth. In this, you have to have your equation solved for y. Well, you've been down this road before. You've heard about implicit differentiation. You know some equations aren't solved for y or couldn't be solved for y. So what do you do when you have equations that you can't solve for y, but you have to rotate them about the x-axis? Cylindrical shells is what we're going to use. Now, the reason why cylindrical shells are going to be a little different is that instead of slicing that volume, you're making those little cuts perpendicular to the x-axis. To find that volume, what you're going to do is you are going to slip cylinders over the x-axis. So those cylinders are going to slip this way, which is going to cut the y-axis perpendicular. So if it cuts the y perpendicularly, I'm not altogether sure that's a word, so don't use that anywhere else but here, you get to use y in the equation. So when would you use cylindrical shells? You're going to use cylindrical shells when you need to rotate it about an axis, but you can't solve the equation accordingly. That gives you another option. Well, we are literally going to be filling that volume with several cylinders. The only way I can describe this is thinking about those Russian nesting dolls. The volume of that outside doll is filled with other dolls. So think about, instead of filling that volume with the same shaped doll, you're filling that volume with cylinders. So some of the cylinders are going to be very wide and squatty. Some of them might be very tall and narrow. But you're filling the area with the entire cylinder itself. So it's not a cross section, it's not a slice, it's a cylinder. So we're going to be filling it with the surface area of a cylinder. Now remember, volume is 3 dimensions. You've got r times h, so there's 2 dimensions, and as always, your integral is going to come up with that third and final dimension. So it's 2 pi r h. 2 pi times your radius times your height. Well, if you're looking at this going through the x-axis here, okay, your radius is going to be that y, and your height is going to be that function. Okay, So you're still going to be looking right to left. Okay, but this gives you another option. You can't have x's inside your integral and you're rotating it about the x-axis. You're going to have to do cylindrical shells. So now we have these options. Okay, if you're rotating it about the x-axis or any other horizontal lines, you've got the option of disc or washer if you want to stay with x's. You can use cylindrical shells, and I have abbreviated that as seashells, soon to be abbreviated as CS. Now you have an option with y's. So you're going to be using disc or washer if you can keep with the x's. You're going to be using cylindrical shells if you can't. This is where you're going to use your y's. So it just opens up a nice little avenue for you. And just like with everything else, just like with your area, sometimes you're going to think, there's no way I would want to do cylindrical shells, and that's fine. Disc and washer may be easier. But there are occasions where you're going to look at it, you can't solve it for x, so your only choice is cylindrical shells. Okay, so if we're doing this about the y-axis or vertical lines, disc and washer, you have your y's involved. Cylindrical shell, it's all about the x. So this way, if they have you do a problem where you're solving it by rotating it about the x-axis and then part B it's rotated about the y, you can use cylindrical shells, and this way you don't need to change your limits. You don't need to change your function. Okay, so it might be easier to do them all so that they're all with respect to x. All right, so let's see what this is going to look like. Okay, we are going to take our y equals the square root of x equals 1, x equals 4, and y equals 0. So when I draw a nice little sketch, and these sketches don't have to be super, super fabulous. I mean, of course, mine are, but, you know, and I'm kidding. So we have y equals the square root of x. We're going x equals 1, and x equals 4, and y equals 0. So the area we're looking at is this area right here. Be sure to shade in that area. We need to know what area you think you're looking at. So there's my volume. We are rotating this about the y-axis. So if we rotate this about the y-axis, okay, my figure is going to look like a weird donut. So it's going to look something like this guy. Okay. So it's going to look like a weird donut. And what we're going to do is we are going to slip cylinders about the y-axis. Okay? So that first cylinder is going to hit us right here, and then the next one's going to be a little wider, the next one's going to be a little wider, 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 wider. So that radius is changing with x. The height of the cylinder is changing with respect to my top function here. Looking at this setup, it would not be difficult for me to go ahead and do this with respect to y and use disc and washers. In fact, what I usually do is I make a little note to myself. I'm going to use y's if I want to do disc and washers. I'm going to use x's if I want to use cylindrical shells. And I just look at the area to see if I would need to change. If I do this with respect to y, I'm going to have to think right function minus left function. In order to do that, that's going to be two separate integrals because I have this top piece and then I have this bottom rectangle. So, no thanks. I'm going to do cylindrical shells because the top function is my square root of x. The bottom function is my y equals 0. I already know I'm going from x equals 1 to 4. I don't have to redo my equation. Seems like a winner to me. When I write this out, I know I'm going from 1 to 4. I've got 2 pi r times h. R is just that x coordinate. So that's going to be x. And then my h is going to be that top function minus that bottom function. So just the square root of x. No quantity squared here because you're taking the radius times the height. And just to make sure, that's my r, that's my h. Once again, just like with all the other pi's, if you want this to come out nicely, take out your pi. So then you're doing 2, and if you're doing this by hand, I would go ahead and multiply that together so that I have something easier to integrate. If you're using your calculator, go ahead and throw it in just like it is. That's going to give us 124 pi divided by 5. Okay, example 2. Y equals x, y equals x squared. Both of these are very nice functions. I could solve them for x just as easily as I could for y. Y is already solved for. So I'm saying, why do you want to change? You've got your y equals x. That's a nice pretty little line there. And then you have your x equals y squared. It's going to be that piece right there. It does come over here as well, but that isn't, let me give you the whole picture. But the only enclosed area is this area right here. So I'm going to shade that in so people know what area I am thinking I'm finding. Remember, you do get partial credit on the AP exam, so it's always best to show everything. It's about the y-axis, so if I do y's, I'm going to have to solve my equations for x. I'm going to be using disk and washer. Disk and washer doesn't seem too bad because the right function is your parabola, the left function is your y equals x. So disk and washer doesn't seem so bad. I can keep x's if I use cylindrical shells. Now I'm going to use cylindrical shells just because everything's already solved for y. It's the first time we're doing cylindrical shells, so of course I want you to practice that. We're slipping those cylinders over the y-axis, so the axis of rotation, those cylinders are coming down this way. So they're going to be hitting right here. So that radius is going to be your x. That height is going to be the distance between this y equals x and this y equals x squared. So top function minus bottom function, that's going to be your height. When I write it out, and I always have to write it out, I need those points of intersection. If I set x equal to x squared in factor, that's going to be 0, and this guy is 1. 0 to 1, 2 pi x, that's the radius, that's how far you are from the y-axis. Your height is x minus x squared. Height is the top function minus the bottom function. Radius is just that plain x. No need to simplify anything if you're putting it in the calculator. I would go ahead and take my pi out, but there's no need for you to multiply anything together. Plug it in your calculator. Don't forget to put your pi back. Your answer is pi over 6. Number 3 here, we're multitasking. We're going to do part A, which is about the y-axis, and then part B, which is about the line x equals 2. Now, right off the bat, I notice this is the y-axis and this is a vertical line, so they're going to be very similar to each other. When I look at my equation, this one I have no choice. I can't solve this for x, so I have to do cylindrical shells. I don't have a choice like I did in the last 2 examples. Well, that's not really so bad because this one works out beautifully with cylindrical shells. Okay, so I do my little picture. It's a nice pretty little parabola. I know it's going to intersect at 0 and at 1. And we're finding this area right here. When I do this about the y-axis, I look at this, I would have to solve it for x equals in order to do disc or washer, cylindrical shells, if I want to keep it with the, ooh, let me back that up, okay. If I want to keep y's in here, then I'm going to do disc or washer. If I can do x's inside here, I'll have to do cylindrical shells. Well, I have no choice in this matter. I can't solve it. Okay, so that guy's off the map. This guy is vertical, so it's the same aspect. It's cylindrical shells. So I'm going to be, for part A, we'll do A in green. We're slipping these cylindrical shells over the y-axis. So that radius is going to be that x every single time. I'm going to go ahead and take that pi out in front. I'm going from 0 to 1. 2 times my radius, which is x, times my height, which is top function minus bottom function, which is x squared minus x, x minus x squared. I had a little dyslexic moment there, sorry kids. Okay. Then I can put that in my calculator. Take that pi out, but don't forget to put it back in. So that's pi over 6. Let's work in black. Now I'm rotating this about the x equals 2 line. So I need to bump that out. So I'm rotating it about this guy right here. So I'm slipping these cylinders on over that line. Now notice the height of my cylinders are exactly the same as the height of those cylinders when I've slipped them on the y-axis. The thing that has changed is the radius. So the radius has changed, the height has not. Okay. My little dx is halfway off my page. Now when I'm looking at my radius, I want you to think about when we rotated about different lines and you had to think about which one had the higher value. If you were doing it with respect to x, you had to look at who had the higher x value. Were you to the right or to the left? Were you above or below? Well, you're thinking about your y guy in this case. So look at where your cylinders are coming from. I'm over here at the 2 mark and I'm working my way backwards. So that area or that radius is going to be 2 minus x. That 2 is farther to the right, so that's going to be the highest value, and we are subtracting our x from there. Okay, so with cylindrical shells, what's going to change when you rotate about a different line is the radius. The radius is the one that's going to be changing, and you need to make sure that that radius is positive. So if your line is to the right of your area, it's going to be the line first, then your area. Okay. So when I put that in my calculator, I end up with pi over 2.